Okay, I think we're ready here. Everyone, thank you for joining us this afternoon. Today we're going to be taking the opportunity to chat with folks primarily in the SPP region about innovations that are underway within power system modeling. So we are with Energy Exemplar. We are the developers of Plexos and Aurora. And the primary focus of this call is just to get folks exposed to what's happening in the modeling world and give you all an opportunity to ask questions and engage with us. So leading this conversation is going to be Stephen Broad. Stephen Broad is our Vice President of Solution Engineering and longtime Plexos expert. And with that, I believe I'll turn it over to Stephen.
Hi there, everyone. This is Stephen Broad. I'd like to welcome you to the webinar. And so as Laura mentioned, we're going to be talking about innovations in power system modeling. So one of the drivers of all of this innovation is what is going on in the industry itself. And there's a constant need for innovation in this kind of modeling. And, you know, it kind of comes down to 4 key reasons, maybe a little bit more, but these are the ones I chose to focus on. So market structures are changing throughout the electric power industry. There are new technologies that are driving some of that change. And increasingly, due to the disruption in this space, people are wanting to see more insights, and they're wanting to see them faster. And also, our various government entities are stepping up with additional regulations to create change in the direction of policy goals that they feel are important. So some of the changing market structures that occurred to me as being of interest to think about, I won't go into any great depth on any of these individually, but these are some that sprang to mind. Things like what's going to happen with the Mountain West RTO? What about flexible ramping, because we need that so badly to integrate renewable resources? What about retirements of various kinds of resources? There's a little map of projected, well, it was formerly projected coal-fired generator retirements. Those were for 2012 to 2016. There's an awful lot of them there. And what happens if we start as a country exporting more liquid natural gas to parts outside of the United States? What's that going to do to natural gas prices? What's that going to do to the overall structure of our electric power economy? And there are many, many, many other kinds of changes to the underlying market structure. But this is certainly driving the need and the desire to model these kinds of power systems. And what kind of new technologies? Well, we're familiar with the new technologies, but they're the usual suspects: renewables, intermittent renewables, or you know, any kind of renewable resource really. Battery storage has had quite a lot of interest in very recent years. Solar plus storage. This chart was taken from a study that was done by the National Renewable Energy Lab about a year ago. And in that study, one of the things that they discovered is that the value of solar is greater, even considering the costs, in many cases, if you add a lithium-ion battery to it. Energy efficiency, distributed generation, demand response products, all of these things are changing the way that we, the structure of the market at one level or another. And one of the things that I think is especially interesting about the business of energy efficiency and distributed generation is that historically our electric power consumption on the utility side was very directly linked to economic growth. But now, because of the fact that we have so many energy efficiency projects and distributed generation resources, some of which are behind the meter, there's a decoupling of overall economic growth from power consumption. So there are a number of different processes that are requiring a rapid pace of insight. IRP for many utilities was optional until fairly recently. A lot of utilities are being required to conduct IRP analysis that they formerly were not required to discuss or to produce to the regulator. And very often the breadth of those IRPs are also increasing. So where once it might have been adequate to do a study that focused primarily on thermal resources, in many jurisdictions, an IRP that doesn't take into account renewables or energy efficiency or other things like that might not be considered to be meeting the standard for that project, the IRP. There's a lot of other kinds of economic analysis, although one that I've been hearing a lot from our customers about in recent years is the desire to do more value at risk analysis. So they want to look at variability, maybe in load or maybe in fuel price or any number of drivers of uncertainty, and understand how much value they may gain or lose simply on the basis of said uncertainty, and how they can reduce the amount of uncertainty in that. And then reliability assessments. These are just 3 examples, but reliability assessments, it used to be quite a common thing to focus primarily on a peak hour assessment for a reliability assessment. But because of the changing structure of the markets and the way in which new resources are being cited, the peak hour may or may not be the most important one to study. In particular, very often it's now periods of high renewable penetration that are very interesting to RTOs to study, because the counterflows or the shift in flow or congestion is just something that we haven't seen in the past, and we have to worry about the feasibility of the grid in such situations. And then there are changing regulatory requirements. There's an awful lot of them. There's RPS targets. There's carbon taxes. There's renewable greenhouse gas initiatives, the RGGI. There are all kinds of energy efficiency programs, and so on and so forth. Any questions about any of those things before we continue on? Hearing none, I'll proceed. So one of the innovations that I think is very important for addressing a lot of these concerns is co-optimization. And I think that a lot of us on the call have certainly heard this word used a lot. And I wanted to take a minute to talk about what co-optimization is and perhaps what it isn't, and what even is really meant by co-optimization in the first place, and sort of talk through some of the aspects of co-optimization. So what is co-optimization? Generally speaking, the idea is that you have a lot of different factors that are involved in a certain kind of economic or physical problem, and you can value each of them. And then what you'd like to do is formulate a single problem that looks at the options, all of the values associated with all of the different commodities that you are considering, whether that's energy or ancillary services or emissions or gas or hydropower or perhaps other things as well. And you want to be able to trade them on an even basis with each other, not in the sense of creating a financial trade, but to be able to swap them. So if in a particular period of time, hydropower is a valuable resource, to conserve it or to get a reasonable price for it. Whereas at a period of time, maybe like in a spring runoff where the hydropower simply needs to be produced, and the value of it is lower, then maybe the value is lower, and you can understand why you might be able to offset some other costs. Likewise, in addition to these various commodities that you may have that have a financial value associated with them, there are also constraints, whether those are transmission constraints or ancillary services supply constraints, or even just energy balance constraints like supply and demand. Emissions constraints on production. You can imagine a lot of different kinds of constraints, including operational ones or the like. And to be able to consider all of those constraints in a single problem is a big part of what co-optimization is about. And when you're looking at all these different commodities, to be able to value them in the same terms. So what might it not be then? Or by contrast to this, what would maybe not be a co-optimal solution? Well, if you are separating the problem of solving a power system up into several different pieces and solving them individually or sequentially, and then iterating on the constraints, this isn't so much a co-optimization as a sequential optimization. Now, it may seem like that is a pretty tight difference, but I wanted to work through why a sequential solution might not be the best sort of thing to do. But first, here's some commodities that you might want to co-optimize. So we've got a lot of different things: ancillary services, energy from various sources, natural gas, carbon, capacity, hydroelectric resources. I kind of mentioned all of those already, but so what could be the problem with solving this sort of problem sequentially? This is the sequential approach at a stage where we didn't have the computing power resources that we have today was commonly used, and because at the time we understood the structure of our systems and pretty well, what we did typically was first do a unit commitment problem, and then assign ancillary services, and then run a transmission problem, and then run hydro, and so on and so forth. And we kind of had an understanding, a very specific understanding of what the linkage between these various steps were. And if at some stage we got it wrong, so say for example, we progressed through this process through to transmission, but then the solution we got from the transmission component of this process said, oh, well, this is going to violate some constraint. Well, then we would go back maybe to the ancillary services step or to the thermal step and go back through. And then we might get here again and violate some other constraint, and then we go back and go through. And that's what's called iteration. The idea of repeating these steps many times to get a solution that's both feasible and optimal in some sense. But there's a number of problems with this. So for example, one of those is the halting criterion, the answer to the question, when do I stop? It's not easy to know how to answer that question when you're looking at a sequential solving operation. And a more important question maybe even is, when I've got a solution, how close will I be to the optimal solution? This process may or may not be able to tell you the answer to that question. And then how close will I be? You may not be able to say that either. In fact, it probably will not. How do I add additional commodities? So I've listed out some things that were typically considered in a sequential solve, but we've got lots of additional things these days that would be added to this somewhere, like battery storage or demand side management or other kinds of resources that might be optimized separately in a sequential solve, but that takes us even maybe a little bit further away from the optimal solution. And it's not clear how I would add those additional resources. I would have to consider each of them on an ad hoc basis. Whereas with a fully co-optimal solution, adding additional commodities, since everything is valued in dollars, it's a very straightforward operation to simply add a new commodity to the model. All you have to do is be able to model it and its interactions with the other commodities that are in your model. So if you wanted to add natural gas co-optimization, you simply need to be able to model the natural gas demand and supply and production and storage and all of those other things, and then explain how the electric power model interacts with the natural gas model, or how the electric power system interacts with the natural gas system in reality. So one of the primary ways, obviously, is that gas-fired power plants burn gas. And that provides a linkage between the gas and the power system. So I mentioned that we had an understanding about how to link these various steps together. And the linkage is what are called heuristics. But heuristics are almost always tuned specifically to match the way that the system worked in the past. And one of the things that I think is important about co-optimization by comparison to the sort of sequential solve with heuristics is that the co-optimization, since it considers everything on equal footing by deferring to the dollar value of the various kinds of resources that are involved, it doesn't have to make decisions like, how will I transition from this product to this other product? It considers them all on a dollar-to-dollar basis. But the heuristic model takes the mechanisms that we assumed in the past and applies them to today, to tomorrow, to 20 years from now. And one of the reasons that we're so interested in doing all of this modeling is because we have this very strong belief that the future and the past are probably going to be different from each other. So the heuristic approach of taking these past performances of our power systems or our generation resources and pushing them into the future means that we may be leaving ourselves open to the possibility that we're not going to detect those market changes in our models. That's one of the most important reasons why co-optimization is so valuable in this context. So just as an example, in a sequential solve like this one, where I first am looking at my thermal resources and then I'm looking at my ancillary services resources, an immediate question that I might end up with is, if I'm committing my thermal resources in step 1 to make sure that I satisfy my ancillary services requirements, and then I'm dispatching my ancillary services in step 2, I may end up overcommitting my thermal resources to satisfy the ancillary services requirement. And then I would go to step 2, and then I would look to see how much that was going to cost me. And then I would have to ask the question, have I got too much ancillary services? Should I have committed less resources? Or do I want to go forward with what I've got and possibly have a suboptimal approach to this? And it's not entirely clear how you would answer that question in a sequential iteration model like this. Whereas in a co-optimal model, this question of iterating or trying to undo what you've already done, it just doesn't even come up at all because it's all solved in a single problem. So another piece of this business of co-optimization is that very often, due to the type of problem you're going to solve, the kind of objective function, the dollar value that you're going to be looking at is going to be derived in different ways. So one kind of scale of problem is this very long-term problem where you've got questions of capacity expansion and resource retirement and production cost, and you're trying to consider all three of those. If I was going to look at that in the context of historical approaches or heuristic approaches, I would be thinking about something along the lines of, well, first let's optimize how much expansion cost I'm going to have, and then I'll optimize the production cost separately. And if it looks like it's too costly, I'll maybe add some more generators. But in a co-optimal model, you'd be looking at expansion, retirement, and production cost all in one pass. So that would be a difference between a heuristic model with sequential iteration versus a co-optimal model that would be looking at the whole thing simultaneously. In the case of reliability and issues of maintenance scheduling or loss of load, very often the objective function is not necessarily the dollar value. In this case, the objective function is usually related specifically to reliability and avoiding lost load. So in this case, I would have a very different kind of objective function because my overall purpose in this sort of modeling is different. And then we have another kind of problem. We've talked about the long-term problem and the reliability problem a little bit, but then we've also got a resource allocation problem. And most people think of this as a budgeting process. So maybe for the year, you've got a specific amount of emissions you can produce, or you've got a certain amount of fuel you can burn, or maybe you've got a certain amount of water you can use for generation. And you just want to decide, how should I apply this resource over the course of a year? That's what I would call resource allocation. And the decision-making process there is one we typically go through maybe on like a monthly basis, for example, rather than an hourly basis. So we're allocating water to January or April or July versus allocating to a particular hour and a particular day. And then we have the familiar security-constrained unit commitment or security-constrained economic dispatch or the standard production cost modeling sorts of things that we do. And that is, again, a different question because in this operational time frame, I'm no longer concerned about, I have already decided which power plants I'm going to build, or I've already decided how much emissions I'm going to allocate to this particular month. And now I want to see when I do that, what kind of scheduling do I get from my generation resources? What kind of congestion do I see in my power system? This is also a place where you'd model day ahead in real time or residual unit commitment markets as well. Any questions about any of those things before I go on? All right, I'll continue. So another thing I wanted to talk about with you a bit was performance. So of course, I mentioned earlier this business about having more computing power than we once did. And so there was a period of time where the idea of a heuristic or iterative model made really a lot of sense because we didn't have so much computing power as we do today. But the primary technique that people use for most of these kinds of modeling today is mixed integer linear programming. And this is computationally intensive and memory intensive. And it's also a well understood mathematical problem. Because it's well understood, we have tools that are available not just for modeling power systems, but for modeling lots of different kinds of optimization problems that are very performant. We also spend a lot of time these days thinking about how to reduce runtime, how to reduce memory use for large models. And the models that we're trying to solve these days are getting bigger and bigger and bigger. So if we were to roll back the clock 20 years ago, the idea of running 8760 power flow plus economic unit commitment and dispatch with the mixed integer programming unit commitment, it just was too big of a problem. But these days, that's something that's very attainable. And a lot of it has to do with these techniques for reducing runtime or memory and also the growing computational power. There's also the question of how to parallelize some of the underlying calculations. Our computing equipment is getting better, but the actual clock speed of the processors flattened out quite a lot in recent years. So a lot of the benefit that we see and a lot of the growth we see in performance has to do with how to split up complex problems into simpler ones so we can solve them simultaneously in a machine with many cores, as opposed to a machine with a single core that goes very, very fast. Well, let's take a look at the question of commercial solvers. I don't know how many of you are familiar with these commercial solvers, but the three leading commercial solvers for mixed integer linear programming are called Cplex, Gurobi, and ExpressMP. And when it comes to power systems, these three products, these three commercial products, provide roughly similar performance. Sometimes one of them will make a little bit of an innovation that gives them an advantage for a period of time, but usually that period is 3 months, 6 months, perhaps. Now, perhaps if you have heard of commercial solvers, or if you've spent some time researching them, you may have heard, for example, that a certain one of these three is really, really good for integer programming problems. Or you might have heard that one of them is better than the others. In the context of power systems, they have similar performance. In the context of other kinds of optimization problems, they typically perform very differently. And part of the reason is because these different commercial solvers have different aims. So, for example, if I was to build a commercial solver to solve an optimization problem, and the most important optimization problem I wanted to solve was how to assign the optimal internet ad to somebody who's browsing Facebook, I would have a very different view of how to do that than I would if I was trying to figure out how to dispatch a combined cycle gas turbine. Because the combined cycle gas turbine, all of the periods of the day are connected to each other. For the combined cycle gas turbine, it may be serving a load that could be served by other resources. So it's coupled to a lot of other pieces. Whereas in the example of serving an advertisement over the internet, there are lots of different choices of which advertisement you could choose, but there's no coupling between them, and not very much anyway. So that the problem of serving advertisements parallelizes really easily, whereas unfortunately the problem of parallelizing power system models doesn't parallelize very well at all, generally speaking. There are ways that we can go about parallelization. I'll talk about that in a minute, but generally speaking, they don't parallelize well. So some of the techniques that certain ones of these are being built to address very specifically are not things that benefit us directly for power system modeling. On the other hand, the three companies that make these products, IBM, Gurobi, and FICO, are constantly innovating on their MILP products. So they're solver products. And we see many updates every year, and sometimes those updates are very substantial. We recently got an update for ExpressMP that was a massive improvement by comparison to the previous version. It had, in some cases, it had a 20 or 30% improvement in the runtime of certain models. So it can be quite exciting to see some of these, the results of some of these commercial solvers come through, and without having to specialize in that particular area, all of you who model power systems are able to reap the benefits of their efforts to give us the latest and greatest in commercial solver optimization. And there are other kinds of non-linear optimization solvers that exist out there. Sometimes people will ask me, what about swarm optimization, or what about holomorphic optimization? And the fact of the matter is that Energy Exemplar, we're always looking at these kinds of techniques. But for now, the performance of those kinds of techniques is still less than the performance of mixed integer linear program, but that's something that we're certainly keeping our eye on. How about reducing runtime and memory use? Well, I mentioned that parallelization was a big factor in that. And so I've noted 3 ways that we go about parallelizing problems. These are ways that you can parallelize problems where the power system model will actually benefit from it. So the first is the parallelization over the chronological period of time. Now, what we do, what we know is that if we tried to parallelize by splitting every hour of the year up into a separate problem, the result of what I would get from doing that would be nonsense, because it could end up with, I commit this coal-fired power plant in hour 1, and then a separate problem decides that in hour 2 it should be off, and the third problem decides in hour 3 it should be on. And since none of those have any knowledge of what's happening in the previous or following piece, they end up with what I would call a discontinuous commitment of that resource in a way that doesn't make very much sense and probably doesn't adhere to its minimum downtime constraint or uptime constraint. So splitting hour by hour or 5 minute by 5 minute might not be a feasible way of going about this, but you could, for example, split up the various months of the year. So if you ran each month separately, you would be able to run those pieces in parallel with each other. Now, the question you'll ask me based on what I just said is, well, what about the end of one month and the beginning of the next month? Could there be a problem there? And the answer is yes, there could be. But by comparison to the problems that would arise if you were to look at every single hour, we've reduced the number of places where there could be discontinuity from every single hour of the year to only a few times a year, only 11 times per year. So that's a reduction. And then if you use a few techniques that we typically use, like looking ahead or behind the period of time where you're focused for a day or two, then you can get even greater continuity between adjacent months. So that's a technique that we'll often do, and that greatly reduces runtime. And then another approach is, say for example, you're running a Monte Carlo simulation. You've got a whole bunch of samples that you're looking to process, and you're running a whole bunch of separate runs with different input data. Well, you can run each of those separately. Now, I don't think that anybody is surprised by that idea, because they are sort of separate, but it just means you need more computing hardware. And then the last one that I wanted to talk about here, at least, is the idea of taking a large transmission system and reducing it down to individual geographies. This is what sometimes is called geographic parallelization or geographic decomposition. And this can create a much better runtime as well, because not only is it parallelizing, but each of the individual problems is mathematically less complex, substantially less complex. So each of the individual problems are running side by side with these different geographies, and each of them take less time than they would otherwise. So it's not even just that you're splitting it into various regional geographies and splitting it into several different problems, but each of those individual problems takes less time than it would otherwise solve. Another thing that we're looking at, and a lot of people are looking at to understand how to reduce runtime and memory use, is to lean more on machine learning. So machine learning is something that people talk about quite a lot, and it provides a lot of power to a lot of areas of analytics. One of the things that's a little bit tricky about it, though, is that the machine learning algorithms are only as good as the inputs you give it. So what we've been doing lately is using the results of fundamental modeling, like a full production cost model or a full transmission run, to learn to understand better how to anticipate what unit commitment and dispatch and what flows would look like and all of these other things in the context of finding similar past runs. So if you have already run a simulation that looks very similar to the one that we're just about to run, we can kind of use that as a starting point for this new simulation. And that's going to reduce the amount of runtime and memory that's required, because it's not going to be doing a full optimization necessarily every single time. Some of the time it'll spend more time leaning on past results. It is, however, important that these kinds of machine learning algorithms are tuned or trained by detailed fundamental analysis, because if they're not, then all you're doing is averaging together things that were perhaps not very well calibrated to begin with. Any questions about any of that before I proceed? Okay. So another thing that's a pretty important component of innovation in power systems is understanding uncertainty in these sorts of systems. And a lot of times people refer to that as stochastic analysis. I would like to draw a bit of a difference between uncertainty per se and stochastic optimization. So many people have heard about stochastic analysis, and most of the time what they're thinking about is what I would call a Monte Carlo simulation, which is certainly a kind of stochastic analysis, but it's only one of several different methodologies for understanding uncertainty. In a Monte Carlo, you take a very, very specific sort of methodology to understand how uncertainty impacts your results. But then there's also another idea called stochastic optimization. And the idea of stochastic optimization, instead of thinking about separating up several different samples, so for example, in a Monte Carlo, you would just have a number of different samples and you'd run each of them individually, and you'd look at the results of each of those individual runs and average them together. In stochastic optimization, the approach is a little bit different. You look at all of the possible samples together at one time, and then make decisions in your model based on all of those possibilities. So I'll talk a little bit more about that in a minute. But what I wanted to start by describing to you is a methodology that we've derived at Energy Exemplar called the rolling horizon methodology. So the rolling horizon methodology allows you to simulate a multi-stage stochastic process. Now, I want to break that down before we go any further, because that may sound unnecessarily technical or perhaps not even like it relates to you at all. But it actually rather closely does. It's just a very different way of talking about it. So very often in power systems or in the utility space, a problem that we have to solve is we're looking at the rest of the year and we're trying to decide how to use our natural gas or coal resources, or how we want to budget out our emissions. And we don't know exactly what's going to happen in the future. We have a forecast of what's going to happen in the future, but we know for sure that probably things are going to not fall out exactly the way they do in our forecast. So we start out by trying to budget to the forecast, but then almost immediately after we start actually living that life, things change. The idea of a multi-stage stochastic process is to simulate the uncertainty and simulate the staging at which we make new decisions based on the fact that reality has happened. So for example, say I had budgeted out my emissions and I had chosen to allocate 20% of it to January and 5% of it to February and 30% of it to March. That's a ridiculously large amount to allocate to just 3 months, but imagine that we did that. And then what happened is that maybe January ended up being warmer than we thought, and I didn't need to use 20%. And then February ended up being colder than we thought, and we needed a lot more than 5%. And then March ended up being warmer than we thought, and we didn't need as much, we didn't need to burn as much coal or natural gas. Well, that's one possible thing that could happen. Another possible thing that could happen is that it comes out almost like what we had forecast, that January is going to be cold and need a lot more fuel burn, that February is going to be warmer and not need as much fuel burn, and that March is going to be colder and need more fuel burn. It could end up being exactly that way. It could end up being the opposite. It could end up being some third thing that where all three of them are about equal. But what we're concerned about in this process is wanting to make sure that we don't make a decision at an early stage in the year that's going to come back to haunt us later. We don't want to over accumulate our emissions allowances, and we don't want to overutilize them either. So when we look out into the future and future scenarios are unfolding in our model, it's going to look and see, oh, should I have made a different decision back a few weeks ago? That's the basic idea here, or a few months ago. And that's what rolling horizon means. It means you keep going forward like 3 months at a time. I look forward to the next 3 months, see what could possibly happen there. And if something doesn't, if one of those is a very regrettable circumstance, we can maybe change our overall planning process to avoid that regrettable outcome. So this is kind of a diagram that would relate to that. So in each of these branches, say for example, we're looking here at this branch, and here's our starting point. And then maybe I've got 3 different ways that this could go in the very first month. And then following on that, I've got 3 different ways it could split out. You could think of this as like high, medium, low, or something like that. High, medium, low, maybe still. And the reason that these have different colors is because it turns out that I'm pretty sure that none of these choices over here are going to be the optimal one. So they're what we call dead branches. So those branches, all these branches here correspond to choices that we could possibly make, but these aren't good choices here. Oops, sorry about that. And then over here on this side, it looks like none of these choices are good either. So those branches are all gray. Now they're still there, but we don't think we're ever going to go down that path. But then it looks like this is the best choice for us in the first month. And then based on that, I've got 3 choices for the second month. And it looks like of those 3 choices, this one is the best choice of the 3. It's the full branch. But I'm still hanging on to these 2 over here. And the reason is that if I go a little further down here, and it ends up being that something really bad happens down here on this side, I might want to go back up to this point and then take a different path. That's what this idea of a rolling horizon and a multi-stage stochastic optimization is all about. Now, the thing about it is that, and part of the reason we do this approach of rolling horizon, is that the further you get down the path, the more moves you're thinking about ahead, the lower the probability of each possible outcome is going to be. So here, if at every stage we have 5 choices, then at the end of the second stage, I've got 25 choices. At the end of the third stage, I've got 125 choices. At the end of the fourth, I've got 625, and I don't even know what 625 times 5 is, but it's a lot. And you can see here on this diagram here that if we were talking about 20 choices or 30 choices, after a certain number of stages, the probability of each possible outcome is really, really small. So it doesn't make sense to go all the way to the end and look at the probabilities of each of them individually, because the probability that any one of those is going to happen is so small that we just don't have any confidence that we could pick the right one. So what we do is we go forward a few steps, and then we look at things that have, a probability that might actually happen, like 0.01%. Now that's, or 0.01%. So that, that's a very unlikely thing, but it's still not vanishingly small. This is a bit small here with 30 choices. But we'd only maybe go forward to the third stage. So if we have this entire horizon that goes through 5 stages, the first time we just look at the first 3 stages maybe. And then after we've looked at the first 3 stages and we've made some decisions, then we would look at the second 3, and we'd move forward one choice. And that means that in this scenario here, I could move back to here and make a new decision. But then once I move forward, this decision is decided and I can go forward from there. And that's how the rolling horizon approach works. Any questions about that before I proceed? One of the things I'd like to mention is that in addition to thinking about things like how you budget long-term things like emissions or hydro resources, if we thought about it on a smaller time scale, like if we thought about it for unit commitment, that makes sense as well. Because I might have the situation where I might have a plant that I want to commit, and if I commit it today, it has an impact possibly for several days. So if I commit it today, I don't want to take it down tomorrow and then fire it back up on the 3rd day. Maybe I would like to look at this in a stochastic optimization view, and that's why we have capabilities around what we call stochastic unit commitment, which is where you're looking at, possible forecasts for the next day to decide based on a path of least regrets what maybe not what the absolute best unit commitment is for the very specific forecast we have, but what a unit commitment is that is both pretty good but also avoids the worst possible things that could happen tomorrow, and anticipates them. So any questions about the stochastic analysis piece before I move on? We have about 12 more minutes. I'll talk a little bit about hydropower modeling. So there's 3 different ways you can represent a hydropower resource. You can look at the hydropower resource as being a limited energy resource, or you could think about the possibility that the hydropower resource was holding back some amount of water. Or you could think about not only the fact that it's holding back some amount of water, but the fact that the elevation of the top level of that water at any point in time varies based on how much water is in the reservoir, and that variation also has an impact on the efficiency of the plant. So those are 3 different methodologies that you could use to think about how the hydropower model would be working. And this is the limited energy version of this is perhaps the most approximate of the 3. The volumetric approach is a bit more accurate, and it allows you to think about not only just the energy production, but also the water flows that result. And then the elevation model allows you to look very closely at how the variations in elevation affect the energy availability of those hydro resources. It's also important, and an important innovation in this space, to think about all the possible different constraints that could affect hydro, not just at the hydro plant itself, although that's pretty important, but also downstream. It takes time to move water from point A to point B. It takes time to, you have to worry about how fast you change the amount of outflow in these sorts of resources. And being able to model those things allows us to have a more accurate representation of hydropower as part of an overall portfolio. And then there's the idea of co-optimizing hydropower resources with thermal resources. So sometimes you can use hydropower resources to avoid the need to start a thermal plant if you do it strategically. And likewise, you can conserve water if the water is very valuable at any particular point in time by running a little bit more thermal resource. So this is a water value-based approach, which allows you to think about hydropower as a commodity that's on even footing with other resources in the portfolio. I sort of alluded a minute ago to the idea that water could flow through a system like this. This system is an example of a cascading hydro system. So here we've got additional constraints beyond simply the capabilities of the resource or the amount of energy behind any given dam, because we've got water that comes from some source and traverses a river system through several different power stations. And the same drop of water is going to be used to produce power 3 times. And what that means is that holding water in one reservoir or another, the water has the most value when it's sitting at the very top of the system, because that water has yet to be processed through all 3 plants, and it can produce value as it does that. But at some point, the water needs to go down through the system and out to the sea, or to whatever subsequent uses it might have. And so being able to represent the constraints that link together any 2 power stations or so on and so forth is quite important to understanding the operational behavior of these sorts of resources. So any questions about any of those things? I wanted to have Laura close with a few words about Energy Exemplar, the company. I hope that you found the content here valuable, and that it gives you some thoughts about how much innovation is required for these kinds of modeling platforms, and what sorts of things we at Energy Exemplar are looking to do in order to make sure you have the best tools available to you. But I'll turn it over to Laura and let her wrap up.
Awesome. Thank you, Stephen. Any questions for Stephen? You can also save them and send them over to me or to Stephen directly after this call as well. So yeah, I wanted to speak just a little bit about the company. I think folks are generally familiar with us potentially, but a lot of exciting things have been happening specifically with our organization. And Stephen, if you'd advance that slide for me. Thank you. And I won't obviously go into all of this. Stephen did a great job of touching upon a lot of the reasons and the layers of complexity that are starting to rear up actively in the market. And so this jumbling of factors that utilities and transmission companies are having to prioritize and wade through have really created the situation that Energy Exemplar finds itself in today, which is a really exciting one, where we have, and again, cue the slide, Stephen, is that we've charted a pathway to address this uncertainty by joining forces with Plexos as well as Aurora. So now the 2 best products in the market are sitting side by side under the same overall product team and data team and an organizational structure that's now internationally planned. And we've done this through partnership with Riverside Company. And so Riverside is really been incredible because it's allowed for significant growth in our products and our teams as well. This started in late 2017, but you'll really have seen it ramped up today. And what's great about Riverside is that it's allowed us to focus on growing the business and the top line and bringing new advancements to our product offerings rather than other private equity firms that you'll see out in the market that are more focused on slimming down in order to just increase the bottom line and then flip. So Riverside is really focused on this growth piece. And the way that that's really translating for our user community is that it's increasing the level of engagement across all points of the user's journey with our products. And so on the next slide, Stephen, I think you went there. So you know, that touches upon sort of all the facets that users are being exposed to with our products, whether that's calibrated and deeper development of our data sets, hands-on implementation services when they're needed in order to get users up and running and analyzing faster, as well as expert support that's soon to be positioned internationally. We've got folks in London and Australia, as well as the US, to support for those, you know, 11 p.m. on Saturday calls, where we'll be having 6x24 support, which is awesome. And then customized training that's really going to be catered to your team's needs and use cases, as well as dedicated account management that's going to allow for sort of a direct line of accountability and collaboration with our development team, where you can access them not only through account management, but also through regular user group meetings and conferences that we hold, where you'll have direct access to those developers. So there's a lot of exciting things that are happening with Energy Exemplar right now that I just wanted to touch upon with you guys. And so I'll open it up again for any additional questions or reflections that anyone might have. But of course, you also have my contact information on the invitation that was included with this webinar. And we'll be holding these throughout the year and ongoing. And so we welcome you to forward these to your colleagues as they continue to pop up in your inbox. And I'd also really welcome any feedback or anything of particular interest, any topics that you'd really like to see. You know, we love to hear back from you guys as to what is actively of interest to you, you know, in our engagements with folks. You know, we understand a bit of that, but anything you'd like for us to talk upon, we are happy to include that in an upcoming session. So with that, I will thank you for your time. Stephen, thank you so much. I've got a lot of digesting to do on this info, and I appreciate it. Thank you, everybody.
It's my pleasure, and thank you everyone for being here.
All right, take care. Have a great rest of your day.